All right, so let's go for it here. This is 5.3. Having gone through looking at definitions for the trig function here, I think we're already set to do this stuff right here. So we're going to start evaluating them, looking at different signs in the different quadrants. And then something about the reference angle. Why do we use it? What's it for? And then finding these trigonometric values just using this reference angle idea here. So define the trigonometric functions now using a unit circle. So far we've been defining these unit triangles, but in terms of a triangle that's sitting on the Cartesian coordinate, right? But it's sitting there, but it's really still a triangle. We want to get off the triangle idea and just make a circle out of it. So a little bit more abstract idea at this point. All right, but anyways, let's go back, just real quickly review. This is on your notes here already here. So I'm looking at it here. So looking at this stuff right here, what we do is we just make a point somewhere out in space. We call it right there. We call it x, y. Ta-da! Now we can always make a line back to the origin, right? And by using the Pythagorean theorem, we can always figure out the value of r. Is that right? And then what we do is we say, okay, well, based upon that, we're also going to make a little angle. We're going to make an angle from the positive x-axis over to this line here. This guy's called the initial side. This guy's called the terminal side of the angle. And with that, we can pretty much make a triangle anytime. And then from there, we define all these, in a sense, what Ptolemy did is he defined all the different possible ratios you can have. We're good? You can have a ratio between the x and the y coordinate. You can have a ratio between the x and the r value. You can have a ratio between the y coordinate and the r value. We good? All these different ratios. So given a coordinate out in space, we can find r based upon this. And so we have these 6 definitions, really, that's all they are. So sine of theta is equal to the ratio of the y coordinate over the r value. Cosine of theta, or the angle, is the x coordinate divided by the r value. We good? So pretty much there are 6 ratios. Tangent, again, is the ratio just of the coordinates themselves, y over x. And then we have the inverses of them. Actually, reciprocals, I should say, reciprocals of each one. So there it is. I think 5.2, hopefully you at least looked at it, at least got the whole concept of the definition of these guys. Now let's go. Let's keep on going. I'm going to skip a few things here just for brevity's sake, but we can look at the examples. I give the examples in the notes right over here. So given -1, 3 out in space, what we want to do is we want to figure out all 6 trigonometric values. So notice we have the x coordinate, we have the y coordinate. The only thing that we're really missing is r. That's really it. So using the Pythagorean theorem, or remember, Pythagorean theorem is a squared plus b squared, right? Is equal to c squared. For us, it changes into x squared plus y squared is equal to r squared. And then the question really becomes, you know what? We're going to be solving for r all the time, right? So why not solve it for r already? So what we do is we just take the square root here, the square root there, and what happens is we have a value now. So that's our formula. We'll just use that formula so we don't have to sort of do algebra. You can just plug in values, simplified, done. All right, so plug in values, simplify, there it is. The r value is square root of 10, and now comes all the trigonometric values. So as you plug it in, notice for sine is the y coordinate over the r value. But then remember, in algebra, we can't keep a square root on the bottom. We like to rationalize our denominators. So that's what we do here. So multiply both sides by square root of 10 and square root of 10. And so it should give us this value right here. Okay, are we good there? Just want to look at one of them. That's about it. All right. Suppose theta is an angle whose terminal side contains the point 2, -5. Find the exact values of all the 6 trig functions of theta. All yours. Notice the funny thing is here, we don't know what theta is. There's no value for angle. We don't even know what that is yet. What we're finding out really in the beginning of the section is that we still can figure out the ratio All right, you can do that on that page, on an extra page, and so whatever you need here, take up as much space as you like. So 5, -2, I'd graph that first. Hopefully you did it here. So 2, +2, -5, that means quadrant 4. Up there somewhere. All right, and then let's do this here. Let's make a little triangle based upon all that stuff. The R value comes all the way back to the origin. Then you have another value that goes back to the x-axis. And then you should have we usually put like a little rectangle piece right here to signify that's a right triangle. So with all that in mind, let's go 2, -5. You guys find me the R value. R value should always be positive. The reason for it is because it's a length from here to there. Perfect, yep. And I'll do it the old way here. You can plug in the formula that I have in the book, that's fine, but 4 + 25 is 29. And then you take the square root of both sides, and you're going to wind up with a square root of 29. Cool. All right, the way the book does it here, it already presents the formula for R, which I think I like even better. So you're not going all the way back to the quadratic formula. And again, a lot faster, I think, to do it this way. And you're done. There's no other way that could be. All right, since we have that, let's go with sine of theta. Again, definition is y over r, y coordinate over r value. Y coordinate is -5. R value is the square root of 29, and just like on the example problem, we got to do a little bit more extra work here. So I'm going to multiply both top and bottom by the square root of 29. And how about -5 square root of 29 over 29 itself? And again, we got to do this 5 more times. So all the different ratios here. Cosine theta, again, x coordinate over r, and you guys tell me if I'm going too fast. The x coordinate is 2, the r value is square root of 29, perfect. And again, do the exact same thing we did before here. Multiply top and bottom by the same thing. Final answer. Tangent, if you have done so already here, again, tell me when I'm going a little too fast here. Tangent is the easy one because you already know the coordinates, so it's the y value over the x value. And we leave it as a ratio, usually in lowest terms. In this case, that's fine too. All right, and then cosecant theta. Again, by definition, it's the r value over the y value. In this case, once you write it down, you're almost done. That little negative there, we don't usually like to write the negative on the bottom of a fraction. So write it in front. You can also write it on top. That's fine too. All right, secant theta, r over x value now, r square root of 29. On the bottom is just a 2, and again, done. And the final one, cotangent theta. Cotangent theta, x over y. 2 over -5. And again, maybe put the negative out in front as opposed to on the bottom. And done. Are we good with those? All right, the next piece, kind of unusual here, maybe you've seen it for the first time, is this whole concept of if the x and y coordinates were in proportion to each other, if it still makes the same angle, what this tries to prove is that it does not matter how far away you are from the origin. If the angle is the same, you're always going to get the same exact ratio for each of these things. So let's take a look at one here. Let's see. Let me just do one sort of quick example here. Let's say our point was right over here. Our point was at 90 degrees. Everybody agreed that that is 90 degrees. And then same thing as pi over 2 if we take radian measurement, right? So sine of theta would be the y over r value. We're good? Again, just using a simple illustration, figure 5.32 more makes sort of like the broad illustration. But the numbers will work out easy here. All right, if that's the case, let's see. If this was 3, if we were 3 away from the origin, wouldn't this guy over here, wouldn't the coordinates really be 0, 3? Everybody agreed there? Because the x coordinate doesn't change, right? It's still 0, so you have to be 3 away. So if that's the case, the y value is 3, the r value is 3, but then the ratio between them is just going to be 1. Are we good? So that means if you were only 1 away from the origin, it would have been 0, 1, and you would have got 1 over 1, which is still 1. Good? So really, interestingly enough here, this means this. It means that if this angle is the same, let's say, maybe let's put some numbers here. Let's say this was a 45-degree triangle. Let's say this was 45 degrees. Then this would have been maybe like 2, 2. Good there? And this would have been maybe like 5, 5. This is 5. Is it still a 45-degree triangle angle? Yeah, it sure is, because we're halfway to 90. So if I say, what's tangent? Tangent would be 2 over 2 for the first one, which still causes a 1 to be there, right? Or we could say tangent is 5 over 5, still a 1. It doesn't matter how far away you are. So really we have this little idea then. Then tangent of 45 degrees is just 1. Doesn't matter how far away you move from the unit circle, as long as that degree is the same, you're still going to get the same ratio and eventually going to get the same value. So then over here we go like this then. We say sine of 90 degrees is always going to be always going to be 1. Are we good? It's always going to be, because the y value over the r ratio is always going to be 1. Okay, with that in mind, let's do the 90 degrees here. All right, so let's go with practice problem number 2. We've got 2 problems here. So then I want to know, find the values of 180 degrees. And again, doesn't matter how far away you move, you're still going to wind up with the same ratio, right? And so maybe let's do this one together, and I'll let you guys do B by yourself. So if this is the case for A, let's see, 180 degrees or pi, where would the dot be? It's going to be on the negative x-axis, is it? So this would be 0 degrees, this is 90, so then 180 would have to be about right there. So if that's the case, here's what I'm going to do. I'm going to make this something called a unit circle. So this unit circle is all the dots that have the length of r is equal to 1. Now, why do I choose this one? Because if r is equal to 1, I don't have to simplify. Remember how we did the square root of 29? Then we had to do all that weird stuff with it? I don't have to mess with that anymore. If r is 1, it's going to be so much easier to sort of get an angle, get a value here. Okay, so there's my little dot. Okay, and the number that I want, we could choose a number. We could choose 3, just like we did before, right? We could choose 7. Easiest one, we're going to try to use r is equal to 1 all the time. So if r is equal to 1, this guy has to be negative 1, 0. We good? Because we defined how far away we are from the origin. All right, if that's the case, I think I know exactly where to put it. So I could put sine of theta, and I'm going to change my angle here all the time. So I could say for this, for A, sine of theta is going to be y over r, which is 0 over 1, which really is just 0. Okay, I should probably use the angle. So maybe like this. Maybe I'll just switch between the angle measurements. I'll put theta, I'll put 180, and I'll put pi, because it wouldn't matter. All right, all yours here. Can you find for me cosine of 180? And again, we're just getting a little bit more abstract than 5.2. 5.2, we were just getting values, and we learned how we actually can get the r value based upon any coordinate out in space here. So cosine of 180, as again, it's x over r, but again, it's already been predetermined for A, so negative 1 over 1, and how about negative 1? And again, this one's very special because this is cosine of 180. So again, no matter how far I go out, right? I could go out to negative 1200 for the r value. Still is going to be negative 1200 over 1200, which will still be a negative 1. Okay, so tangent, I'm going to use the, let's see, the radian measurement for it here. So tangent of pi. And again, y over x in this case, and y over x 0 over negative 1, in this case just 0. All right, good there, maybe. Cosecant theta, r over y. Ooh, this is no fun. R over y is going to be 1 over 0. So sometimes we could actually have undefined terms. Sometimes there are no values for them. Secant of 180 degrees, again r over x. In this case, it's going to be 1 over negative 1 this time, but still negative 1. And last one here, cotangent. Cotangent, I'm going to put the pi value in there. And again, I'm just changing the angle around. It doesn't matter what it says, either pi or 180 degrees or theta. Hey, there's another one here. Another one that's undefined. So I guess for these trig functions, sometimes they will be undefined. Actually, let's go back even further. Can sine and cosine ever be undefined? I don't think so, because you're never going to be at the origin, right? You're going to be at a certain place outside of the origin. So cosine and sine never becomes undefined. But all the rest of them, especially when you have the denominator be a coordinate here, these guys are safe because our denominators are. So tangent could be undefined sometimes. Cosecant, secant, and cotangent, these guys could all be undefined at certain times. Okay, that was A. All right, crossing out that one. And letting you guys try B here by yourself. All right, and let me start as well here. So I'm going to make a X and Y grid here, Cartesian coordinate plane, 270. All we got to do is figure out where that is. And again, we're going to put it on the unit circle. We're going to put on a circle where all the values are r equals 1. So it'll go down here. Hope you guys made it there. All right, and again, we're going to define the r value ourselves because, as we looked at, the distance away from the origin wouldn't matter at all. So we're going to use the easiest number possible, which is 1. All right, if that's the case, if we're 1 unit away from the origin with an angle measurement of 270 degrees, that means this has to be 0, -1. Are we good there? All right, if that's the case, I think we're almost done here. So sine of theta is -1/1 or just -1. Right. I'm going to stop putting the definitions down. Hope you guys remember it. If not, should go in a little something called a 3x5 card, right? But you should have it memorized eventually. So our cosine, I'm going to put 3 pi over 2, again, just to make the angle measurement more defined. It doesn't matter. You could put cosine theta, you could put cosine 270 degrees, all that is okay. But really got 0 over 1. In this case, just going to be 0. Hope you guys got that. Kind of fun little divide symbol there. Tangent of 270 degrees would be y coordinate over x coordinate. In this case, the tangent value is undefined. All right, cosecant 3 pi over 2. Again, you could use any one of these here because theta or 270 or 3 pi over 2, they're all the same thing. And how about -1? And secant theta, hopefully you put it in there here, or secant 270 degrees would be undefined as well. And cotangent of theta would be 0 over -1 or just 0. All right, out of curiosity, how many got all 6 correct? Sweetness, all right. Another question, how many looked at 5.3 prior to coming to class today? 1, 2, 3, whoa, 4. I don't know if that's record or not. Okay, so there's that. Notice all these guys are something called quadrantal angles. Remember, all the way back to 5.1. Remember, quadrantal angles are angles that end on an axis. And so what the book says, look, if we keep on going, if we looked at 90, and we looked at 180 as we did, 270, went back up to 360. If we did that and kept on doing that, here's what we have. We would have this right here. And it's just kind of a little table. Anybody know what page number it is on in your textbook? Sorry, 503, okay. Again, just growing old here. Ears are not working like they used to. Okay, 503, that's where we're at. So sine, notice sine is never undefined. Cosine, never undefined, but it switches back between 0, 1, and -1. Both these do. And then for the tangent, cotangent, secant, cosecant, kind of funny. For tangent and cotangent, it's either 0 undefined. Secant, cosecant, it's 1, -1, or undefined. So again, you guys will get used to these here as well. All right, next topic to look at is something called coterminal angles. Again, there's what it talks about. Coterminal angles are where the terminal side ends at the same spot, but the angle may not necessarily be the same. Maybe a graphic will be better to sort of see it. So I have this angle here. So P is x comma y. There's my r value, and there's my theta value. Well, coterminal just means, how about this? How about if I go all the way around and then still get to this point? So how about if I do this? That's theta 1. I'll put theta 2 right over here. So theta 1 went from the x-axis to the terminal side. Theta 2 went actually 1 revolution around and then still went a little bit more. But is it still going to be the same ratio? Still should be the same ratio though. And so what we have is we have this little we say that sine of theta 1 is going to be equal to sine of theta 2. All that just means that the ratios are going to still be exactly the same. We can keep on going. That's sine. Cosine is also going to be the same. Tangent is going to be the same. Cotangent, cosecant. All right, how do we do that in terms of just numbers themselves? Let's take a look. So notice it's going to be 1 full revolution around, right? So if you think in terms of degrees, what really are saying is this. If I have an angle right here, I'm going to get the same exact value as if I added multiples of 360 degrees. Okay, does that make sense? So if we're at 45 degrees, and we say tangent of 45 degrees is 1. Anybody, what's 45 plus 360? So tangent of 45 degrees is equal to 1, and then it's the same thing as tangent of 405 degrees. All it's still going to be 1 because the ratio is still going to remain the same. All right, now the only thing is what gets a little tough is trying to do it with radian measurement. Now remember, the full revolution in radian measurement is just 2 pi. Because pi is 180, so therefore 2 pi will be 360. Can you also go towards the negative side of things? Yes, right? You can go backwards on those angles as well. All right, so let's go for it here. Maybe take a look at deal with the numbers. What did it actually mean in terms of numbers here? So here's what we got as our example here. We're trying to figure out the sine of 2,580 degrees. Don't want to draw that out, but I'm thinking, okay, hold on. How many revolutions of 360 do we have? And so as we divide maybe 360 into 2,580, we find out it is 7 plus something, right? It's maybe 7.2 or something like that. So we say, okay, that's cool. So that means there's 7 revolutions of 360, and now the only question is, what's the extra stuff? And the extra is what we need. So once we figure that out, we say, okay, that's it. You know, instead of putting 2,580, it's going to be the same thing as sine of 60, which is square root 3 over 2. Okay, are we good there? Pi works a little different. Pi, you got to think of in terms of 2 pi. So let's take a look at an example here. Okay, cosine of 17 pi over 4. Now this is where the trick comes in here. Remember, it's 2 pi, is that right? But you have a denominator of 4. So the question is this. If you're taking multiples of 2 pi, but you have a denominator of 4, how many is that going to be? And so really what you do is you think of multiples of 2 times 4. You can use 8 pi, right? 12 pi, 16 pi. Yep, that's 16 pi. It's the closest one without going over 17. So that means it's 16 pi over 4. That's the 360 degrees for us. So the leftovers are pi over 4. And so again, cosine of 17 pi over 4 is the same thing as cosine of pi over 4, which is this right here. Let's take a look at some examples here for us, or practice for us here. Cosine 1,830 degrees. Whew, that's fun. So I've done this kind of several different ways. It seems like the easiest one, if you don't have a calculator handy, because you're not going to take, okay, 1,830 degrees divided by 360. If you don't have that, then it's a little easier just to do multiplication. And it's probably best as you get used to the numbers. So let's see, 360, and then let's take a guess here. Maybe it's times 2. Is that close to 1,830 without going over? And I think we have some space to go. So then let's say, okay, how about it? Maybe it's just 3 times as much. And again, multiplying that out gets you 18, gets you 1,000. So 3 revolutions is a little bit over 1,000. 4 revolutions, multiplying that out is, as you multiply, is a little bit under 1,500, just so we sort of have this sort of comprehension of things. That's getting close. And then multiply by 5. So 5 revolutions is, ooh, I like that, 1,800. It's close, but not going over yet. So I think I got what I need here. So let's see. Cosine of 1,830 degrees is the exact same thing as cosine of 30 degrees plus 1,800, which I know to be 5 revolutions anyways. And again, if you want to do the rest of this, that's fine. What I probably do, I would not do kind of go around the horizontal method. I'd probably go like this. I'd probably just underneath it write cosine of 30 degrees. Because I know it's already 5 revolutions. I did the math already. So cosine of 30 plus 1,800 is really the cosine of 30. Now I've got to figure out what is cosine of 30 degrees. Because we only did quadrantal angles. Alright, so this is where hopefully you guys did 5.2 well. So here's 5.2 stuff coming at us. It's going to be, there's my X and Y grid. 30 degrees is about right over here, right? It's sort of like the third of the way to get to 90. Make myself a little triangle, the R value coming out to the point. Top part being dropped down. All right, think back to 5.2. Here it is. It's going to be a 30, 60 triangle, right? What is the value of a 30, 60 triangle? If the R value here is 1. Talked about in 5.2 here. $60 degrees, the opposite of the 30 degree angle is always going to be 1/2. The opposite of the 60 degree angle is always going to be √3 over 2. All right, those of you that's still having sort of a hard time with 5.2. This comes off of this whole concept of, from geometry, of the equilateral triangle. So the question over here, just as a quick aside here, what happens if you have an equilateral triangle and each of the sides are 1, 1, 1? Hey, what are each of the angles going to be? 60, right? You got 60 here, 60 there, and you should have done this in geometry sometime if you had a good geometry teacher. Okay, so what we do is we split this guy in half like this. Boom. We're good? So that means this guy now is 30 degrees instead of 60, right? But then if you took half of a triangle, is this going to be 1/2 right here? So this is kind of coming off of a equilateral triangle being cut in half. Now the question is, what in the world is this piece right here? And if you do a little bit of Pythagorean theorem, which is we did in 5.2, we find out that this is √3 over 2. So anytime you have a triangle, no matter what shape it is, as long as this hypotenuse is 1, and it's a 30, 60, 90 triangle, the side opposite your 30 is always going to be 1/2, and the side opposite your 60 is always going to be √3 over 2. Okay, no matter which way it's facing. We can actually face it like this even. Come down like this, and you kind of tell where the 30 degrees and 60 degrees should be. That means the 30 degrees has to be on top here, 60 is here. As long as the hypotenuse is 1, opposite my 30 is always a 1/2, opposite my 60 is always √3 over 2. Good there? So when you form your triangle, when you write this in, you got 60 degrees here, and opposite of 30 is 1/2, perfect. Opposite 60 is √3 over 2, okay. And if the R value is 1, that means the X value has to be √3 over 2, the Y value has to be 1/2. That's how you get that point right there. So critical. And that's why we only really have values for multiples of 30 degrees and multiples of 45 degrees. So we just cover the 30 degrees. Okay. And then the other part that's interesting too, remember how cosine is defined to be the x over r value? It's the ratio, right? But hold on though, our r value is 1. Do we even need to do anything about it? So let's say this, the cosine is root 3 over 2. And then do we really need to divide by 1 later on? Sorry, got it. I don't think so. So it just stays as, so if you're on the unit circle, we really don't need the r value at all. Okay, the tough part here, sine of 31 pi over 3. Okay, let's erase this one. We didn't do that one. All right, I'm going to go just a little bit faster here since we've seen these here. So sine of 31 pi over 3. The question now becomes is how can I simplify that, or what simplifies here? So, okay, I've got to think of 2 pi, right? 2 pi, but we have a denominator of 3. So really every 6 pi over 3 is a revolution. Does that make sense? Let me go over here. So each revolution is 2 pi, right? But this assumes a denominator of 1. We have a denominator of 3 in our hands. So now I got to think, okay, what's the numerator going to be in order to have 1 full or complete revolutions of stuff? Well, it's just going to be a multiplier of 3, right? So multiplier of 3 gets us, okay, so we're looking at multiples of 6 pi. We're good? So give me a multiple of 6 pi that's less than or equal to 31 pi. Yeah, 5. 5 times 6 is 30, so 30 pi over 3 technically would be the answer. So I think we got it here. Sine of, so if it's 30 pi over 3, that means I have an extra pi left over, and then I have 30 pi over 3 over here as part of my revolutions. Are we good there? So I think radian measurement, you got to get used to it a little bit here, but I think it's even simpler than degrees, because we can multiply 6 times 5 a lot faster than 360 times 5. Cool. Okay, again, what I would do, I'll probably just drop this out like this, boom, completely out, done, and go from it. If you really want to see how many revolutions you have, that's fine too. You may actually have need of that. So 10 pi, so again, you know it's 5 revolutions, but I would write it like this. I would write just, it's just sine, blah, 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 that one, not even that one. I would write this one here, sine of pi over 3. So I would probably go from here down to here automatically. If I don't need the number of revolutions inside here. Okay, sine of pi over 3. So let's take a look at this one here now. Again, x and y grid. Pi over 3, pi over 3. Anybody know how many degrees is pi over 3? I heard 60 in a whisper. I go with that. Yep, it's going to be 60 degrees. So I draw my little dot over here, about 60 degrees-ish. Draw my r value back to the origin. Then I draw my altitude down to the x axis. And again, I know this guy to be pi over 3, or really 60 degrees there. Let me make it a little bit bigger just so we can kind of see stuff. That's 60 degrees here. 30 degrees is over here. And we know this guy to be 1. Can you put in all the other values? And then can you give me the coordinates then? by the time we're done with trigonometry, you're going to know these values memorized here. You're going to do enough practice with them on the homework, and you'll know them.
Does it change anything if you just do how many times 3 goes into 31? Because you get 10. Does it change any of your stuff there?
That's cool too. You can do it that way. Understanding that once you get 10, you know it's 10. You still have to do the still have to figure out that it's just one more than 10. And that way it's easy, yeah. Okay, so opposite my 30 is a 1/2, opposite my 60 is √3/2. Therefore, the coordinates that I have here would be, and again, it's going to be this bottom value. That's technically your x-axis is going to be the x-coordinate here. So 1/2. Going up would be √3/2, and for the sine value, it is y-coordinate over r. We can care less about r because r is 1. We care about this guy over here. So how about √3/2? Okay, we're in practice problem number 3. We still have a little ways to go here. We'll jam. We're good. We got 2 more things, and a lot of it will be more practice items, though. Now let's take a look at signs of these trig functions here. So that little 30, 60, 90 triangle is going to help us, but we got to know then if we're going to be in quadrant 2 or quadrant 3 or quadrant 4, what do we look for as far as signs are concerned? Or actually, can we go backwards through this little exercise? In quadrant 1, everything is positive, right? So let's go back to our coordinates first. The x and y coordinates, they're going to be positive, positive. In quadrant 2, things change, right? In quadrant 2, the upper left-hand corner, the x-coordinate is negative, the y-coordinate's positive. So in that case, if we think about this here, that means cosine and tangent are going to be negative here. So let's not focus on the negative. Let's focus on the positive. Sine is going to be y over r. So in this case, sine and cosecant, but really we want to concentrate on sine. Sine is the one that's going to be positive in quadrant 2. If we dip down to quadrant 3, that's when you have the x-coordinate and the y-coordinate both being negative. In that case, sine and cosine will both be negative, but negative divided by negative is a positive, so that's funny. In quadrant 3, tangent is the only one that's going to be positive. Of course, cotangent is going to be as well, but it's just the reciprocal. Cool. Boom. Cosine in quadrant 4, yes, it will be, huh? Because the x-coordinate is positive, y-coordinate is negative, so that means sine will be negative, tangent is negative, cosine actually will be positive. So we have this little idea here. So you have, if you start with quadrant 1, you say A, S, T, C. My trig teacher, he said, well, nice acronym for all students take calculus, right? Everybody here is going to take calculus? No. See, that's not true. So then I had a class of kids that were just stealing calculators all the time. So I said, all students take calculators and don't return them. That's still not true either, because not all of them were thieves, just a few. So I don't know how you guys want to do this. Some people say cats, C-A-T-S, as you sort of go backwards. That's cool too. But anyways, in quadrant 1, all of them are positive. In quadrant number 2, you got sine, then you go tangent, then you go cosine as far as being positive. So let's take a look at it real quick here. There's an example problem here. Can you guys tell me which quadrant are we in if tangent is positive and cosine is negative? And this is the way I like to figure it out. I kind of draw this scale already. And I ask myself, okay, hold on. When is tangent positive? You guys give me the 2 coordinates. Tangent is positive for the 2 quadrants. We know all of them are positive here, right? We know that's true, right? And then the other one, which is, as Idro said, was 3. Okay, so there it is. We've checked this one out. Boom. So now we go to this one here. When is cosine negative? Well, it's positive here because all, right? All students. So hold on, that's so cosine is going to be negative here, and it's also going to be negative here because it's positive over here because of the x coordinates. So which one fulfills both criteria at the same time? Quadrant 3 is the one that fulfills both. Good. So yours for your practice problem here. Give me the quadrant that gives you sine being positive, but cosine being negative. All right, hope you guys did this here. Let's see. Cosine being positive. Well, I'm sorry, sine being positive. Of course, quadrant 1. And again, of course, quadrant 2, because of what we talked about earlier. When is cosine going to be negative? Yeah, or you can think of it in terms of x and y values as well, right? Remember, because cosine is really technically the x value. The x value is negative left of the y-axis. So 1 and 3, in this case, that means quadrant 2 fulfills both at the same time. Okay, so let's go on a little bit more complicated. Let me give you one trig function, give you a sine of another one. Can you find the rest? That's what we want to look at here. This, let me go to here. So given that tangent theta is negative 5 over 4, and we know cosine is positive, now you guys get the easy one here. It just says find sine theta and then secant theta. Again, just because we're in a little time constraint, let's do this one together here. So first things first, we got to figure what quadrant we're in, right? Just like we did before. So tangent theta is equal to a negative. Oh, okay, hold on. So when is tangent theta negative? Which quadrants? Perfect. 2 and 4, is that right? It's positive in 1 and 3. When is cosine greater than 0? When is cosine positive?
4.
Quadrants 1 and quadrants 4, so therefore we are in quadrant 4 based upon just the signs of our trig functions here. So quadrant 4 it is. Cool. So now let's actually draw it out. So we know that we are in quadrant 4. And then let's think about this here. So that means we have a positive x value, which is 1, 2, 3, 4, 5, because we're just trying to figure out where, this is what we're trying to figure out. This little negative, does this negative belong to the 4 or the y value, or does this negative belong to the 5 or the x value? Well, because we're in quadrant 4, we just figured out A belongs to the y value, because we're going to go down. So that means it's 5 to the right and 4 down. That's where we're at. Out of curiosity, are we on the unit circle? Are we on the circle that's only 1 unit away? Not at all, because notice the unit circle will be right here, right? Here's your 1 unit away right there. There's your unit circle. That's when r is equal to 1. So because we're not on the unit circle, we have to figure what r is. So I know I am at 5, negative 4. And so that little previous exercise of finding which quadrant, that was just to get us to the quadrant. You guys tell me, what is going to be the R value? Can you guys calculate the R value for me? Again, it's not what I got here. I think you were subtracting instead of adding. 41. I go with that here, yep. So remember, we're going to square 5. We're also going to square negative 4 in here. So how about a 25 plus 16? Good there? Because the negative times the negative is going to go away. So how about a 41 inside a square root? Cool. Once we get to this point, I think the rest is easy, right? Just figure out, okay, which trig function we need. We need sine. So sine of theta is going to be, now since we're not on the unit circle, we're going to say it's going to be the y value over the r value. All right, and of course we have to rationalize our denominator here. So how about negative 4 root 41 over 41? Secant, by definition, is, let's see, the x value, I'm sorry, r value over the x value. So r value is square root of 41 over the x value, which is a positive 5, and that one I can stop right then and there. So that's interesting. If I know the signs, or at least I know which quadrant I'm in, if I know the value of one trig function, I can pretty much find all the rest of them. Okay, one other concept we have to learn just to make our life easier as we go later on with this stuff here. Something called the reference angle. Sometimes it's called theta prime. It's listed here. But it's really what's the angle that's formed by the terminal side in the x-axis. And it helps us here. All right, so let's take a look at 4 different possibilities. Possibility 1, what happens if it's in quadrant 1? If we take a look at this here, theta, the angle itself, is actually also the reference angle, or theta prime. They're the same exact thing, because this terminal side, the angle that's formed between the terminal side and the x-axis is theta over here. Good there. Next, what happens in quadrant 2? If I'm trying to figure out the reference angle, or I'm trying to figure out the real angle, let's say this theta here crosses into quadrant 2. The question is, what's the angle that's being formed from the terminal side back to the x-axis? Well, it's going to be this one here. And then what's the relationship between this and this? Well, let's see. Isn't that just going to be what we need to get in order to get to 180 degrees still, right? What we're missing. So in this case, the reference angle is going to be 180 minus theta. Right there. Okay. Let's go on here. What happens if you go past 180 degrees in your quadrant 3? If you go backwards here, so the reference angle is going to be, really it's going to be how much more you went beyond 180, right? So if in terms of just computing, so reference angle equals theta minus 180, because we're a little bit past 180. Okay, and the last one here, if we're in quadrant 4, we're almost at 360 degrees, not quite, so the reference angle can be found by saying, okay, if we were at 360 and we're going to subtract out the angle itself, we would get the reference angle here. So we're not quite at 360. So there's those. Let's take a look at a few. Now this is in terms of angles only, but again, we have to think about radian measurement as well as we take a look at these here. All right, let's jump to our practice problems here. Okay, can you find for me the reference angle in each one of these? problems here. Then I have an extra part for C, because I think I needed. Start here. So with A, 175 degrees, that is almost getting to 180, but not quite at 180. So really what we have, there's 90, 180. We are here. And you can almost sort of guess what the reference angle is going to be here. Yes, we are 5 units away, right? Or 5 degrees away from 180. We could just put 5, but if you want to sort of do the algebra method here, we pick the formula we need. So in quadrant 2, it's 180 minus theta. In this case, 180 minus 175, which would give us, again, 5 degrees. And of course, just to make your life difficult here, let's go to radian measurement. For B, part B, it is 5 pi over 3. So the only crucial point we got to think to ourselves is, where in the world is 5 pi over 3? All right, so students do one of two things here. They either convert this back into degree measurements. That's okay to do, except then you're really not learning how to do radian measurements here. Or we think of this here. We think of, in our mind, just real quickly, we say, okay, pi over 3. We have these little quick references here. So if you say pi over 6, what you're saying is you're saying 30 degrees. Pi over 4. Anybody? 45 degrees. And pi over 6. Oh, sorry, pi over 3 is 60 degrees. We're good? And so if you think of it that way, it's really 60 degrees times 5, or 300. That's kind of quick sort of ways to do it. Or you can sort of do it this way here. If you say, okay, 60 degrees is going to be about right here, right? So this is, technically, this is pi over 3, 2 pi over 3, 3 pi over 3, right? Yeah, 3 pi over 3 is pi, which is 180 degrees. 3 pi over 3, 4 pi over 3, 5 pi over 3 would be right there. So we are in quadrant 4. And that's all we really needed. We needed to figure out which quadrant we're in. Because if we're in quadrant 4, then the formula says reference angle is 2 pi minus the theta itself. Say again?
3 pi. Or pi over 3.
Yes, perfect. So getting a common denominator, I think, here, at least putting in the angle first here, 5 pi over 3. Common denominator would be 3, so how about a 2 pi now becomes 6 pi over 3? Subtract 5 pi over 3, and final answer of just pi over 3. Okay, those are reference angles. Again, we'll make our life a little easier as we go. All right, I threw in an extra little problem. It says C with a little star next to it. Just want to try this one. This was not part of the practice problems of the textbook here, but I wanted you guys to sort of see it before you get to your problem here. So looking at this here, you got to think about, or at least have radian measurements, right? You got pi over 2, right? You got pi, you got 3 pi over 2. You know the pi values, but what happens if there's no pi values in the radian measurements? So this is what we sort of think of. We think of 3.14. 1.57. So it's half of 3.14. then we say what's 90 plus 180 would be 270. So 3.14 plus 1.57. Or doubling 3.14. Doubling 3.14, full revolution would be 6.28, sorry. Okay, and then we add 90 plus 180, or 1.57 plus 3.14, which gives us 4.71. So in terms of radian measurement, once you see it, you should be able to sort of tell where you're at. So 5.75, quadrant 4, right? Because that's all I really need to know. I need to know which quadrant I'm in. I'm in quadrant 4. So that means I have a whole turn right here. That's called theta. So then can you give me the value of the reference angle? All right, there's my reference angle. Again, the formula would be 360 minus theta, right? Or in this case, it would be 2 pi minus theta. So how about just this right here, right? You're not quite to 360 degrees, right? So you're going to take how much is 360 and subtract from the angle that you have. And once we do that, we wind up with the reference angle is 0.53. Good there. Okay, so part C is all yours here. I think it's on the next slide over. All yours if you want to try it yourself. This is the true part C over here. 8.22 is the value. So if we're thinking 8.22, oh, hold on, we're going to go even beyond 360 degrees, right? So this is what we did last time. The question is it just a little bit beyond 6.28? So it's in quadrant 1. Does it go really even beyond that? Jumps all the way back into quadrant 2. Right, so then I'm going to do this. I'm going to keep on adding 1.57 or an extra 90 degrees to each one. Right? So I ask myself, okay, I'm at 6.28. If I add another 1.57, what am I going to get? I'm going to get a 7.85. That's still not enough, right? So I'm going to add another 1.57, another 90 degrees to see what this angle would be. And if that's the case, there it is. I find myself that if I went all the way around back to 180 degrees, really what I have is 9.42. So at least I have it. I'm in quadrant 2 now. All right, since I'm in quadrant 2, here's the way I draw what I got here. I go like this. I go all the way around the unit circle, and then I go all the way up to this. So I'm saying, look, I went one full revolution already, but what's my reference angle? I go with 1.20. We're not quite, we passed 3.14, right? We're not even talking about that anymore. We actually are getting close to 9.42. That's the problem. So then really what the reference angle is going to be 9.42 subtract 8.22. And when we do that, we get ourselves at 1.2 1.2 or 1.20, it doesn't matter. Any one of those is just fine. Okay, 7, we're gonna all right, put this all together here. How do we work it out? So this is practice problem number 7. It says this: find cosine of 1020. And again, we really are putting the 5.3 pieces together finally. Okay, so we got 2 problems here, putting them together. So how do we find cosine of 1020? Well, first of all, 1020 is a big number, right? So we could do it by the what we learned earlier about how many revolutions we have, right? And so we say, okay, well, 360 times 2 is 720. That's cool. And then maybe the next one here. Let's see, 360 times 3. And if you do that multiplication in your head, you wind up with us going a little bit too far. So we say to ourselves, well, that's a little bit too far, so we can't use 1080. We'll have to use 720 as our number. So that means there was 2 full revolutions and then some. So if we subtract that out, we get 0, 0, and how about a 300? Okay, I'll wait for you guys to catch up on that one here. So here's what I got. I have cosine of 1020. Now it becomes cosine of 300. So now let's start thinking about the reference angle here. That's what we want to consider. Before we do that, let's see. Is cosine positive or negative in quadrant 4? Positive, we good? Because I know we're in quadrant 4, because we're all the way over here, like this. So what's my reference angle? Are we okay with 60 degrees there? Okay, so here's the play that we're gonna do. We just need to figure out cosine of 60 degrees. Once we do that, we just need to think about the sine of where it's at in which quadrant. Because the sine is going to be determined in which quadrant it is. Remember how we said the angle measurement doesn't matter? It's always going to be the same no matter what. So here it is. Because cosine is in quadrant 4, because cosine is positive in quadrant 4, cosine of 300 is the same thing as cosine of 60. Now, if we were in quadrant 3, we've got the reference angle. All we would do is we put a little negative sign in front of cosine at this point, right? Good there. Because we'll have a negative sign there. Okay, let's finish it off here. Let's see. I just need to figure out what in the world is cosine. So notice what I'm going to do. I'm going to translate this into quadrant 1 right away, because I just need this right here. So can you guys tell me what in the world is cosine of 60 degrees? Go with that. If we work a little bit out here, let's see. If it's 60 degrees, that means that's the angle that's formed between the terminal side, right, this guy, and x-axis. What is always opposite my 30 degrees? 1/2. Opposite my 60 degrees? Cool, okay, and then if you want to, you can actually put the coordinate, that's fine. Coordinate would be 1/2, right? That's the x coordinate, that's the stuff that takes you from the origin to the right. Then the y coordinate, but cosine only deals with the x coordinate. So finish it off. I'll give you a hint, it's not going to be the square root of 2. I'll give you that 1/2 there. And again, that would be a good one to sort of practice and think about those values here. Let's do 2 more problems here, just because we're running low on time. I'm going to show you one where it's going to go to a negative value instead of a positive value here. So let's do practice problem number 8, just part A only. So find the exact value of cosecant of 1035. Practice problem number 8, we're trying to figure out cosecant of 1035. And you should know this already. Let's see, it's going to be multiples of 360. 360? 720, is that right? What's the next one after 720? 1080, is that right? Yeah, 1080, okay. So if you multiply by 2, you get 720. Multiply by 3, you get 1080, so therefore there's no point to go on. Therefore, our angle that we want, that'll get us back to 1 revolution instead of 2, is going to be 5. Let's see, 1, 3. So let's see what we have. Cosecant of 1035 is the same thing as cosecant of 315. Do you need parentheses there? You don't. I don't know why I put those in there. Okay, so 315. If we look at this here, we are in quadrant 4, is that right? We're about right here. So now the question is, what's my reference angle? How much do you go from 315 to get you to 360? You need an extra 45 degrees, huh? This is 315. 315 plus 45 gets you 360. Therefore, our reference angle is 45 degrees. Okay, how do we work this? Cosecant. Cosecant positive or negative in quadrant 4? It's negative, because the cosecant is the reciprocal of sine, right? And sine is positive in quadrants 2 and 1. Therefore, cosecant has to be negative in quadrant 4. So this is what we're going to do. We're going to say this. The next line equals, important here, negative cosecant of 45 degrees. That's what reference angles are made for right there. So if you get to the point of using reference angles a lot, you really just need to know the values of your trig functions only from 0 to 90. And that's it. So you don't need to memorize all of them all the way around the unit circle. Okay, here we go there. That's a major mental transition right there. Cosecant of 315 is the negative cosecant of 45 degrees. Okay, now let's talk about this one here. This is mentioned in 5.2, but the answer will be, okay, the negative comes from here. Cosecant of 45 degrees, that's going to come from the R value over the Y value, or even better yet, it's going to come from this right here. It's going to come from, see if I did it right, a 45, 45, 90 triangle. Whenever you see a 45, 45, 90 triangle, one of the ways from geometry we always write it is like this. So if your angle measurement is 45 degrees, that's theta that I'm using. Opposite your 45s are 1s, and your hypotenuse is root 3 over 2. So then we say to ourselves, okay, cosecant is r over y. Therefore, r is root 3 over 2. That's my hypotenuse. My y value is 1. Right there. So that's the other triangle. We had a 30, 60, 90 triangle. This is the 45, 45, 90 triangle. So if you find this on your notes here, this is the unit circle definition. So we talked about the fact that if you're on the unit circle, r value becomes 1. So originally, the sine function is y over r. But if r is equal to 1, this just becomes y. So whenever we have the r value, those just became 1. Again, x by definition is x over r. If r is defined to be 1, therefore it's just x. So if you know you're on the unit circle for a cosine, you just look at the x coordinate and you're done. Okay, tangent, again, same thing. Tangent, again, all these guys are now just r is equal to 1s. This did not affect tangent and cotangent. That's the only two that did not affect because r was not in any of those two. But remember, this was r over y before. That just becomes 1 over y. Secant was r over x. Now it just becomes 1 over x. So how do we deal with this? Let's take a look at one example. All right, so let's go with this here. It says find, let's see what are we looking at? Find sine, cosine, and tangent given 7 pi over 6. So this is also in your textbook. It's called the unit circle chart. It has the degree measurement, the radian measurement, and it has the x and y coordinates. This one, again, a good little chart to sort of see things here. So we are in t is equal to 7 pi over 6. So if we look at this chart here, we're going to go wrap around here. This is pi over 3, 2 pi over 3, there's pi. 7 pi over 6 is going to be a little bit further than that. There it is, 7 pi over 6. Technically, it's 210 degrees. So can you give me sine, cosine, and tangent? That's it. It's just the sine of 7 pi over 6. It's going to be that right there, which means it's going to be the y value, or the y coordinate, at 7 pi over 6. This is the easiest way to do it. Yes, you look at a chart, you look at it, and you're fine. Like all the other stuff we do need to have in our mind here. Okay, cosine of 7 pi over 6 is going to be just the x coordinate, so negative 3 over 2. And tangent is the one we got to sort of work it out with here. It's going to be the y coordinate over the x coordinate. All right, so let's see, negatives would cancel each other out, I believe, right? Negatives are gone. And you guys remember from geometry? Remember from geometry, whenever you have a complex fraction and the denominators are both the same, so denominator here is 2, the denominator here is also 2. So these guys would cancel out. So common denominators inside a complex fraction will cancel. If that's the case, I have this, I have the 1 from the top, I have the root 3 from the bottom, and I just have to rationalize my denominator again here. So root 3 over 3, on both sides here, and eventually how about root 3 over 3? That's no fun.